in the last lecture, we had derived certain equations from where we can deduce how to combine three rotation axes which meet at a point in 3 dimensions. And the solution that we had is presented here on the slide, where I have three rotation axes A, B and C. Axis A has a rotation of alpha, axis B has a rotation of beta, and axis C has a rotation of gamma. Then we formed this spherical triangle which the interior angles are alpha by 2, beta by 2, gamma by 2, and the angles between the axes, between let us say A and B is the angle C, between A and C the angle is B, and between the axes B and C the angle is A. So, the equations out here give us how the alpha, beta, gamma are related to the angles A, B and C. And we had solved one specific problem of three two-fold rotation axes meeting at a point. Then the only way they can meet is when the angles A, B and C are all 90 degrees. That means the two-fold rotation axes are orthogonal to each other. Now, in this lecture, let us take a little more general case. Let us say that I have a combination of axes n to 2. So, I have an n-fold axis and then the other two axes are two-fold rotation axes. And I will put the n-fold axis on A, the other two folds will go on B and C, which means I have the axes A 2 pi by n is the rotation angle and the other two rotation axes are B pi and C pi. So, if I have to let us say now find out the angles A, B and C. So, I have my alpha as 2 pi by n, beta equals gamma equals pi. Substituting in the three equations, cos of A would be equal to, clearly if I substitute these angles out here, it will be cos of pi by n, and that is not implies that angle A is simply pi by n. Cos B would be equal to cos C and the result is 0, which means that the angles B equal to C is equal to 90 degrees. So, I have this solution to the more general case. So, now let us figure out for different n values what are my angles, angle A, B and C will always be 90 degrees. So, if I have a two-fold rotation axis n is equal to 2, I am going to have an angle of pi by 2 or 90 degrees. This is the same result when we combined three two-fold rotation axes in the last lecture. Three-fold, it would be pi by 3 or 60 degrees. Four-fold, pi by 4, 45 degrees, and then the last crystallographic axis, a six-fold axis, would give me value of A as pi by 6 or 30 degrees. So, essentially what this is telling us is this angle A, if you look at, it is the angle between B beta and C gamma. In our case, beta and gamma are 180 degrees pi, which means basically angle A is the angle between the two-fold rotation axes, while angles B and C are essentially that all the two-fold rotation axes will make a angle of 90 degrees with the 2 pi by n axis. So, if I consider let us say now n is equal to 3, n is equal to 2 we have already solved last time. So, n is equal to 3 means that angle A is 60 degrees. So, if I pictorially draw this, So, I have a threefold rotation axis. I have drawn this vertically. So, I have one two-fold rotation axis, a second two-fold rotation axis, but remember that this is a these axes are at 90 degrees to the three-fold axis, and this three-fold will generate a third one as well. And this is the diagram in which all the two-fold rotation axes are in a horizontal plane, making an angle of 90 degrees each one of them with the three-fold rotation axis, while between the angles, between the two-fold rotation axes, the angles are 60 degrees. So, this in fact is one three-dimensional point group that is presented here, and it's, if I want to put the notation for this, the notation for this is 3 2. So, there are only two characters that are used here. This is for the same reason that we had 3 m as a point group in two-dimensional group, same thing 3 2, because there are all the two-fold rotation axes are related as a result of the three-fold rotation axis or rotation of 120 degrees around the three-fold rotation axis. Now, consider now another value of n. Let us consider n equals 4. So, now I have a four-fold rotation axis around which I will have several two-fold rotation axes. So, let me try to draw this. So, again these two-fold rotation axes will be at 90 degrees to the four-fold rotation axis. Again the two-fold rotation axes are in the same plane. This time the angle between the two-fold rotation axes would be have to be 45 degrees, while the two-fold rotation axis will be perpendicular to the four-fold rotation axis. So, this is another point group which we can give a notation of 4 2 2. Next, let us consider n equals 6. So, now I have a six-fold rotation axis around which I am going to have now several two-folds rotation axis perpendicular to this four-fold rotation axis. Okay, this is a rough kind of a diagram in which the two folds are again at 90 degrees to the sixth fold, while the angles between the two folds are 30 degrees. And this particular point group we can give the notation 6 2 2. So, these are some of the axial point groups in which only rotations are involved. Let us now try a different combination. Let us try a combination of three axes like 6 4 2 combination. So, I have a six-fold rotation axis, a four-fold rotation axis and a two-fold rotation axis. So, again I have basically A 2 pi by 6, B 2 pi by 4 and C pi. So, I have alpha is equal to essentially 60 degrees, beta equals 90 degrees, and gamma to be equal to 180 degrees. So, what is going to be cos A? Again, we plug in alpha, beta, gamma into these equations to get our A, B, C, and what I am going to get is cos A to be equal to root 3 upon 2 upon 1 upon root 2, and this gives me square root of 3 by 2. Similarly, if I were to calculate for cos B, then cos B will be equal to root 2, and cos C would be equal to root 3. Now, what is wrong with these numbers? Well, all of them are greater than 1. That means we cannot have any angles A, B, C defined for these numbers, because we know that cos has to be between -1 and +1. Hence, this combination is not possible, or I will simply call it as an invalid combination. So, no such point group can be formed by the combination of 6, 4 and 2-fold rotation axis. Now, let us consider a couple of more combinations. Let us consider 2, 3, 3. So, in this case alpha equals pi, beta equals gamma equals 2 pi by 3. Now, if I were to find the angles A, B and C by substituting alpha, beta, gamma in those equations, I am going to get A to be equal to 70.5 degrees, I will get B to be equal to C equal to 54.7 degrees. If I look at 4, 3, 2, another combination, let us look at 4, 3, 2. In this case, alpha equals 90 degrees, beta equals 120 degrees, gamma to be equal to 180 degrees. Then I am going to get A to be equal to 35.3 degrees, B to be 45 degrees, and C to be 54.7 degrees. Just it may help if I draw how these rotation axes are getting combined. So, I will draw this spherical triangle. So, this is A pi, so 2-fold rotation axis, and out here I can put B 2 pi by 3, 3-fold rotation axis, and C 2 pi by 3, which is also a 3-fold rotation axis, and the angles are labeled as A, B and C. Similarly, 4, 3, 2, look at this combination, this is A 2 pi by 4, so 4-fold, then B 2 pi by 3, 3-fold, and C pi, and these angles are small a, small b, small c, the angles between the rotation axes. Now, what kind of a object can have this combination of rotation axis? So, here I will give you one example of such an object. So, out here they are basically cubes. So, the object which can accommodate 2, 3, 3 combination and 4, 3, 2 combination is essentially a cube. So, here I have drawn the diagram on the right, where I have 3-fold rotation axes which are along the body diagonals, and the 2-fold rotation axis is along the parallel to the cell edge. So, if I look at the various angles, when I say A in 233, A is 70.5 degrees, which is the angle between the two threefold rotation axis. So, that angle could be referred to between the two-fold rotation axis as 70.5 degrees. Angle B and C are basically angle between the two-fold rotation axis and the three-fold rotation axis, and that angle is 54.7 degrees. So, there you have it, this combination will fit in the cube. Now, if I look at the 4-3-2 combination, now I have four-fold rotation axis parallel to the cell edge or the cube edge, and the three-fold rotation axis still remains along the body diagonal, while the two-fold rotation axis is now joining midpoints of two opposite edges. Now, in this situation also you can write down the various angles, and you can see that the angle between the two-fold and the three-fold is 35.3 degrees. The angle between the two-fold and the four-fold is 45 degrees, which is more obvious, and the angle C between three-fold and four-fold is difficult to show here, but yeah, it will be something like this, and that is 54.7 degrees. Now, we can let these axes operate over each other. We can let these axes operate over each other. So, for example, the three-fold will bring the two folds along the different parallel to different edges, and there will be a three-fold along all the body diagonals. Similarly, in the case of 4-3-2 also, when we let one rotation axis operate over the other rotation axis, I will have four folds parallel to all the cell edges, I will have again three-fold along the body diagonals, and I will have two folds along all pairs of from the joining midpoints of all pairs of opposite edges, and that can be seen in this diagram out here, where you can see that in the case of 2-3-3 combination, I have the two folds parallel to the cell edges. In the case of 4-3-2, I have four fold as parallel to the cell edges or perpendicular to the cube face, while there is a two fold joining midpoints of every pair of opposite edges. Now, the point group that is labeled the 2-3-3 combination, the point group is called 2-3, only 2-3, again for similar reasons as before, and 4-3-2 for the second case. Now, just a little bit of caution here, that if I go to N2-2 combination, I had labeled this as 3-2, while this is labeled as 2-3. So, two different point groups, the only difference in the notation is one is 3-2, the other is 2-3. Now, let me consider another combination which is going to use a rotation axis and a mirror. So, let us take a three-fold rotation axis and a mirror perpendicular to the three-fold. Let us draw a motif number 1, which is right handed. 3-fold will rotate this motif by 120 degrees. This motif, let us say, is somewhere here, and another 120 degree rotation will take us to a new position 3. So, this is 2 right handed, this is 3 left handed, and all the 3 motifs are in the same horizontal plane above the mirror. This mirror will reflect, the mirror will reflect the motif, the 3 motifs. So, let us say it gets reflected here and it becomes left handed. So, let us say this is motif number 4, or let me first label this. Motif number 1 will get reflected, I will call this as 4 left handed, I will put a comma inside to show that. Then this is another motif number 2 gets reflected down, this is motif number 5 which is also left handed, and similarly motif 3 will get reflected and this is also left handed, and let us call this as 6 left handed. Now, let us take one particular situation where I have motif 1 right handed goes to motif number 2 right handed through an operation of 120 degrees, a 2 pi by 3, 2 goes to 5 which is left handed through a reflection operation. Now, how can I go from 1 to 3? Now, 1 to 5. So, 1 right handed to 5 left handed. Now, this is where we come to another symmetry operation that I just barely mentioned it earlier as roto-reflection or roto-inversion. Now, this is a 2-step operation. Just like a glide plane has a 2-step operation, this is also a 2-step operation. One way to go from 1 to 3 is to rotate motif number 1 by 120 degrees, you come to motif number 2 and then reflect. Now, this is what we call as roto reflection symmetry, and this is also a point symmetry operation because there is one invariant point which is at the intersection of the mirror and the 3-fold rotation axis. But there is an alternative way of looking at this, which is rotate motif number 1 by minus 60 degrees and then do an inversion, then perform an inversion operation. So, that is called as roto inversion. So, rotate by 120 degrees, reflect, we use the notation, since it is 120 degree rotation, we use the 3-fold notation. So, 3 as the notation, and on top of that we put a curl or a tilde on top to represent that this is a 3-fold roto reflection. If I look at the second case, here the rotation is 60 degrees, therefore, the correct notation should be 6 and a bar is put on top to show that this is roto inversion. So, this is roto reflection and this is roto inversion. We will use roto inversion. Otherwise, these two operations give you the same result. So, therefore, we will say that 6 bar is equal to 3-fold roto reflection, but this is the preferred operation for us. So, from now on we will not talk about rotoreflection, we will only talk about rotoinversion. Now, how many rotoinversion symmetries can be there? Well, take all the crystallographic rotation axis. So, I will have 1 bar, 2 bar, 3 bar, 4 bar and 6 bar. So, these are all the crystallographic roto inversion symmetries possible. Now, what I am going to do now in the next lecture, I am going to devise first a better method to represent these 3-dimensional symmetries, because drawing these 3-dimensional diagrams can be very confusing at times and also very tedious. So, we have to come up with a better way of representing these symmetries on a 2-dimensional plane. Thank you.